We're going to talk about the transformer, which is an application of alternating currents used to step up or step down voltages in order to transfer electricity long distances. So we have an input alternating current and an output alternating current, and in the middle we have a soft iron core which is wrapped on the left hand side by the primary coil and on the right hand side by the secondary coil. Now, because we have a coil here and we have an alternating or a changing current, we also have a changing magnetic flux in the core, because the magnetic field is transferred through the soft iron core, and it's constantly changing direction due to the fact that the direction of the current is also constantly alternating. If we didn't have the soft iron core there, if it was broken, then it wouldn't transfer the magnetic field around. And due to Faraday's law, in the primary coil, because there's a change of flux, the induced EMF in the primary coil, epsilon P, is going to equal the it's the rate of change of magnetic flux linkage, which is the number of coils, which is NP, times the rate of change of magnetic flux. Similarly, in the secondary coil, because there's a changing magnetic flux and we have numbers of coils, the induced EMF in the secondary coil is going to be the number of coils in the secondary coil times the rate of change of magnetic flux. Now, the rate of change of magnetic flux is the same in both coils due to the fact that they're connected through this soft iron core. So by substituting, or I can divide equation 1 by equation 2, because this is a system of simultaneous equations, I get epsilon P over epsilon S equals NP delta phi over delta T divided by NS delta phi over delta T. And the delta phi's over delta T's cancel. I end up with what we call the transformer equation, which is the ratio of the EMFs in the primary to the secondary coil is the same as the ratio of the number of coils in the primary to the secondary coil. And by a little bit of rearranging, you can also convince yourself that the ratio of the EMF in the primary to the secondary coil is the same as the ratio of the number of coils in the primary to the secondary, but it's inversely proportional to the current in the secondary to the primary coil. Now, in order to step up the voltage, therefore, if I want to have a larger voltage in the secondary coil than I do in the primary coil, then I have to have more turns in the secondary coil than I do on the primary coil. But by stepping up the voltage, I'm stepping down the current. And vice versa, if I want to step down the voltage, I have to step up the current.